In the previous video, we looked at the physics behind why there's voltage across a forward bias diode. And again, the amount of voltage we have across a forward bias diode primarily depends upon the material that it's made out of. In this class, we primarily consider silicon diodes since they're the most common type of diode. So the forward bias voltage that we'll be using will either be 0.6 volts or 0.7 volts. Now, in this picture here, over on the left, this is a plot of the IV relationship for an ideal diode. Just like you learned in circuits that elements in your circuits, your basic circuit class EE321, were defined by current voltage relationships. For example, resistors are defined by Ohm's law. Okay, current equals voltage divided by resistance, or voltage equals current times resistance, as you know. Opens and shorts are also defined by current voltage relationships. A short has 0 volts across it, no matter what the current through it is, and an open has 0 current, no matter what the voltage across it is. Also sources. An ideal voltage source has a constant amount of voltage, no matter what the current is, and an ideal current source has a constant amount of current, no matter what the voltage is. So those are just a handful of examples from your 201 class of IV relationships that define electrical components. Well, it's the same in electronics, that electronic devices are defined by current voltage relationships. So here's a plot that defines an ideal diode, that when it's forward bias, it acts like a short, and a short has 0 volts across it, no matter what the current through that short is. So that's what that vertical line represents. When an ideal diode is reverse bias, well, that's what this horizontal line represents, that it acts like an open, since a reverse bias ideal diode will have no current no matter what that reverse bias voltage is. So as we said, a diode is essentially a voltage controlled switch. When it's forward bias, it acts like a switch that's on. When it's reverse bias, it acts like a switch that's off. So it only allows current to flow one way, and that's anode to cathode. Well, in the actual case, here's the IV curve for the actual case. And the big difference, like we talked about, is that there's a depletion region that first has to be overcome before current will freely flow through the diode and be limited only by the resistance that's in the diode's path. So if you take a look at this IV relationship and compare it to the ideal case, you can see the differences. Over here on the reverse bias side, this IO, that's that small amount of reverse bias current that we're not going to worry about. So again, in this class, we're just going to assume that the actual and ideal cases are the same in the reverse bias region. Okay, we're not going to worry about this reverse bias current I0, which is typically microamps or even less than that. Okay, the big difference is right here on the forward bias side, that this V gamma, that's the forward bias voltage. Okay, that's the voltage that's dropped across the diode to overcome that barrier at the junction that we talked about last video. And you see in between a small amount of forward bias voltage and this V gamma, which is the forward bias voltage of the diode, and this is also called the turn-on voltage. Okay, we think of once we have that barrier overcome at the junction, that the diode has turned on, so to speak. And that just means that now current's going to flow through only impeded by resistance in the path of the diode, that the barrier is no longer providing a hurdle for current to flow through the diode. And you can see that this in-between region here, where we have this exponential curve, well, that's the fashion of which that barrier is overcome. Like I mentioned last video, it's overcome in an exponential type of fashion here. So in this region between 0 and the turn-on voltage, the V gamma, which again would be 0.6, 0.7 volts for a silicon diode, well, that's when the diode is kind of on. It's not fully on, but it's not off. Okay, current is flowing through, but it's still being impeded somewhat by that barrier. Now in this class, we're not going to concern ourselves with this region here between when the diode is reverse bias and when it becomes fully on. Okay, this kind of on region It does have some applications, but the majority of applications for diodes is that you want the diode either off, reverse bias, or you want it totally on, okay, where there's the turn on voltage dropped across it. So we're just going to look at applications where we're either off or we're totally on. We're not kind of on, okay? But just like in the ideal case, in the actual case, the diode acts like a voltage controlled switch, that as long as you forward bias such that the turn on voltage is dropped across that forward bias diode, it's going to act like a switch that's on, and when it's reverse bias, for all practical purposes, it acts like a switch that's off. And again, it's only going to allow current to flow one way, which is anode to cathode. So let's see how we're going to handle actual diodes in analysis. And the real key point to understand how we represent actual forward bias diodes is looking right here once the diode fully turns on. Once the diode fully turns on, if I was to extrapolate this curve here, for all practical purposes, it would be a perfectly vertical line. Okay, I mean, in reality, it's going to have some slope, but you know, it's going to be a very steep slope. So for all practical purposes, I can say that once the diode becomes fully on, it's going to have this constant amount of voltage across it, okay, 0.6, 0.7, no matter what that forward bias current is. Now, this is assuming we're within the power rating of the diode, because, you know, if this current got such that, you know, it was large enough, well, it would eventually overheat the diode. But as long as we assume that we're within the power rating of the diode, I would have a constant amount of voltage across that diode when it's forward bias. Okay, so say 0.6 volts would be constant no matter what this current is. Well, that's the definition of a voltage source. Remember from your 201 class that a voltage source has a constant amount of voltage no matter what the current is. And you see in this region here of this plot, that's what the diode is acting like. So that's how we're going to represent an actual diode when it's forward bias. We're going to represent it as a voltage source of value V gamma, okay, a value of what the turn on voltage is, what the forward bias voltage is. So let's go ahead and look at some examples here, some of which we've seen before in the ideal case. In fact, here's the very first diode circuit that we looked at that just had a 1.5 volt voltage source, a 1K resistor, and a diode. And we saw at that time that given the orientation of this diode, it was forward bias. We got that with the ideal diode model, making the reverse bias assumption, okay, as we did in one of the first videos. And you know, we know, or we saw that current flows like this, right? Because current's going to flow anode to cathode through the diode, and it flows from the plus side to the minus side of the source. And the amount of current here would just be 1.5 volts divided by 1K, which is 1.5 milliamps. Okay, so we did that. Well, the only difference in the analysis when we treat the diode as actual is that once we find that the actual diode's forward bias, and we would still use the ideal diode model with the reverse bias assumption as we did previously. Well, now when we replace the diode symbol for the forward bias actual diode, we replace it with a 0.6 voltage source. Sometimes in some of the homework problems in the book, it's replaced with a 0.7 volt source. So either one's fine. Okay, in reality, it's going to be somewhere in between there. Like if you actually hook a diode in an actual circuit, say in the lab, you know, the forward bias voltage is going to be somewhere between 0.6 and 0.7. Okay, but in analysis, we use one of the two extremes. And in my lectures, I mostly use 0.6. In the book, you might see 0.7. Now, when you put this voltage source symbol to represent the forward bias actual diode, the plus side of the source always goes to the anode. Okay, and that's because when current flows through a diode, you're going to get a voltage drop. Okay, as current flows through, as this forward bias current flows through the diode, you drop voltage. So that's why the higher end of the source goes to the anode, since that's the end that the current's entering. Okay, diodes can only absorb power, just like resistors. See, if you had this the other way, if you had the cathode on this side, well then that would imply, or excuse me, if you had the minus side of the source here and you put the plus side on the cathode over here, I'm sorry, this would be the anode based on how we put it in the circuit. But if you put this source in such that the higher end of the source was on the cathode, that would be implying that the diode was supplying power, which can't happen. Okay, diodes cannot supply power. So we represent actual forward bias diodes as a source that's absorbing power. Okay, so now if you find this current, well, it's just going to be 1.5 minus the drop across the diode, the 0.6 divided by 1K. Well, you're going to get 0.9 milliamps. Okay, so look, your forward bias ideal current's 1.5 milliamps, and your actual forward bias current is 0.9 milliamps. And that's always going to be true. It's always going to be true that your actual forward bias current is going to be less than what your ideal forward bias current is, right? Because in the ideal case, you don't account for the drop. So it makes sense that that should be more. Okay, but that's always a check you can do, because if you end up with more current in your actual case than in your ideal, you know something's not right. Now, here's a problem we did earlier in an earlier video, and you can look back and see that we got an answer here for the current, and the current was flowing like this, right? Because again, forward bias current always flows anode to cathode. So that current that we found came out to be 3 1/3 milliamps. Okay, that was the ideal forward bias current for that diode in this circuit. Well, if you want to get the actual forward bias current, the only difference is now you put in a 0.6 volt source, and again you'd put the plus side of that source on the anode, okay, and the current's still going to flow like that. Now I'm going to leave this up to you, and in fact this problem was in the review problems, the 201 review sheet at the very beginning of the quarter, or what I made available at the beginning of the quarter as a review. At the time, you know, you didn't know this represented an actual forward bias diode. You just thought it was some 0.6 volt source, but in reality, that's what it was representing. So if you did that problem correctly, you saw that the current through that 0.6 volt source came out to 2.93 milliamps. Okay, so you see that's the actual forward bias current, and again, it's less than what the ideal was, so it makes sense. Alright, one last problem in this video, and that's this one here. And this is the problem we did earlier for the ideal case. When we treated this forward bias diode as being ideal, and we had a short where this 0.6 volt source is, we found that the current for the short, or the ideal forward bias diode, came out to 6 2/3 milliamps. Okay, because if you just imagine a short here and you do a KCL to find the current through that short, well, the current through this 1K is going to be 20 minus the 10 volts on this side divided by 1K, and then minus the current through the 3K, which would just be 10 over 3K, you know, if we had a short here instead of a 0.6 volt source. And again, this was done in an earlier video, so you can go back and look at that video if you have any questions about where this 6 2/3 milliamps came from. Okay, now we're going to do the actual. Okay, well again, the difference is we have to account for the voltage drop across the forward bias actual diode, this 0.6 volts. So now this current through the 1K, it's not going to be 20 minus 10 like in the ideal case, it's going to be 20 minus 10.6, right? Because you see these two voltage sources are in series, so their voltages just add between this ground node and the node here where the 1K, 3K, and the plus side of the 0.6 volt source connect. So you see this is going to be 20 minus 10.6 divided by 1K. And then you're going to subtract that from the current through the 3K, or excuse me, you're going to subtract this current through the 3K from the current through the 1K. And the current through the 3K has 10.6 volts across it, divided by 3K. Alright, and if you work out these numbers, you'll see that the actual forward bias current comes out to, oops, it comes out to 5.86 milliamps. Okay, so again, the actual forward bias current is less than the ideal case. Alright, next video we're going to look at LEDs, light emitting diodes, and then we'll move on to Zener diodes from there.